Hey, what's up everyone? Welcome to Thermodynamics Part 3, where today we're going to be talking about enthalpy. And enthalpy is like a really important topic in thermodynamics, and we'll see how it has applications in the rest of thermodynamics. And I'm going to try to fit as much information as I can into this video. So let's just get started with what enthalpy is. Enthalpy is going to be all the energy in a system. And so all that energy is going to include the internal energy, so how much energy it has internally, and all the energy required to have that system exist in space. Sometimes we don't think about it. Think about the system, like the energy it takes for that system to exist, right? Like this water bottle, I use this water, like I don't know why. It's like the first thing that's next to me. I use this water bottle for like every example. Basically, if this water bottle is taking up some space in the universe, and the space that it takes, it needs energy to do that. So if we're trying to calculate enthalpy, it would be the internal energy plus PV. And PV represents pressure times volume, and that represents the amount of energy required to have that system exist in space. And so it's actually really hard to measure enthalpy, and in fact, we can't do it. And the reason why it's like a really nice analogy that I heard of is like trying to measure all the water in the ocean. There are just so many weird pockets where water can be that we can't really accurately measure all the water in the ocean. And similarly, there's so many places where energy could be in a system that we just can't measure it. So what we can do is measure the change in enthalpy. And I use this analogy in the entropy video, but essentially if someone's in line waiting to pay for something and you see that they're being charged $4, you don't know how much money they have in total, you don't know how much is in their bank account, but you do know that they are $4 less rich. They have spent $4, their change in money is -4. And so one of the simple things that we can do right away is relate enthalpy to heat. So the change in enthalpy under constant pressure is going to be the heat of the reaction. And I don't like this definition a lot because you're going to notice soon that the change in enthalpy is going to be in the units energy over mole. And the unit of Q, which is heat, is just going to be some energy unit. And we'll see why that becomes kind of a problem in this practice problem. Burning 48 grams of graphite in excess oxygen under the standard conditions releases 1,574 kilojoules of heat. What is the change in enthalpy of CO2 gas? And at this point, you might just be thinking, okay, I'm just going to go with A, right? Because we know that the change in enthalpy is the heat of the reaction at constant temperature, and that's what we're told. But that is not true. You can't really trust that. And the reason why is because the change in enthalpy is in terms of moles. If we write out the reaction, well, graphite is just carbon, and that G doesn't represent a gas. I'm just too lazy to write out graphite, and it's in excess oxygen, and it produces CO2. And so if we have 48 grams of graphite, that is how many moles of graphite? That's 3 moles of graphite. So 3 moles. And so if 3 moles of graphite are used, then that means 3 moles of CO2 are going to be formed. So although we have 1574 kilojoules of energy, 1574 kilojoules of energy are in 3 moles. And so if we're trying to find energy per mole, we would just divide this value by 3 and we would get 394. So our answer would be C. And we are correct. But now you might notice something interesting, right? I got a positive value here, but the answer was a negative value. And it's not because the answer is wrong. It's because we haven't introduced the positive negative thing truly yet. So change in enthalpy is relative to the system. So if you have a negative change in enthalpy, the reaction is going to be exothermic, and if you have a positive change in enthalpy, the reaction is going to be endothermic. Think about it, right? If you lose energy, a change in enthalpy that's negative relative to the system means that you have lost energy. If I spend money, it's analogous to spending money, I have less money. If I get in more money, then I have more money. And so spending money is like a negative change in enthalpy, and getting money is like a positive change in enthalpy. So for some examples, if the change in enthalpy were negative 890.1 kilojoules per mole, that'd be exothermic. But if change in enthalpy was 73.8 kilojoules per mole, that would be endothermic. Now, there are a couple types of enthalpies that I want to go over. And the first one is going to be enthalpy of reaction. So the enthalpy of reaction is the heat energy absorbed or released by a chemical reaction at constant pressure. It's sometimes referred to as the heat of reaction. And so if you have a heat of reaction that is negative, that's going to be exothermic. If you have a change in the change in enthalpy of reaction, if that's positive, then obviously that's endothermic. You can actually represent these energy changes visually. So if you have an exothermic reaction where your change in enthalpy is negative, well, your energy of your reactants would start out about here. These would right here would be your reactants, and then you would go down in energy as you went to products. But how does your potential energy change as you go from reactants to products? Well, it follows this curve pattern. And this is true for basically all reactions. And so that top here is like a transition state. From the reactants to that transition state is what's known as the activation energy. activation energy. And from the reactants to the products, that is your change in enthalpy. It's important to mention the labeling of the axes. So on the left-hand side, or on the y-axis, you have potential energy, and on the x label, you have the reaction coordinate. The reaction coordinate is like as the reaction progresses. And so we just saw what happens to a exothermic reaction. Let's see what happens to an endothermic reaction. In an endothermic reaction, you start off with your reactants somewhere, and then since you have an increase in energy, the level for the products is going to be higher than the reactants. So remember, for this one, the products were underneath the reactants, but in this case, the products are going to be above the reactants because you have an increase in energy. And so the same thing would happen here. You would have that curve that's going to be higher than both the reactants and the products. And your activation energy this time is still going to be from your transition state all the way down to reactants. That's going to be your EA, or activation energy. And from your reactants to your products, that's going to be your change in enthalpy. The last thing I want to go over concerning the enthalpy of reaction is something known as Hess's law. So Hess's law allows you to manipulate chemical equations and their change in enthalpy values based on what you do. So if you have a forward reaction like this, where A plus B results in C, and that has a positive change in enthalpy, if you wanted to reverse the reaction, your change in enthalpy would just be a negative. So you can see in this case, it's C is going to A plus B, and all we had to do was negate the sign over here. What you can also do is multiply the entire reaction. So in this case, in the first one, we went from A plus B to C, and in the second one, we went 2A plus 2B to 2C. And as you realize, the change in enthalpy from the first reaction to the second reaction is just doubled. And so whatever stoichiometric coefficient that you multiply the whole thing by is what you multiply the change in enthalpy by. The last thing you can do is add them together. So if you have A plus B results in C, and C plus D results in D plus F, well, these C's are going to cancel out, and you're just left with A plus B results in D plus F, and you just have to add these two change in enthalpies to get the final change in enthalpy. So obviously these aren't real reactants and products, like for the sake of simplicity, but for reactions with actual reactants and products, the fundamentals still work the exact same way. And I want to look at a problem where they give these generalizations. And I really like these generalizations because it helps you learn them without having to write out all the chemical formulas and whatnot. So given the enthalpy changes, and we're given three equations, what is the change in enthalpy of the reaction 2A plus B plus D results in 2F? So the first thing I like doing in these things is seeing which ones are only in one reaction. It kind of doesn't make sense until you kind of look at it. For A here, well, A can come from reaction 1 or reaction 2. And this would be reaction 3, I guess. And so we can't really start with A. B, on the other hand, is only in equation 1. And so since we need 1B on the left-hand side, then we know for a fact that we're going to need one of the first reaction. We also now know that we're going to have 1A coming from the first reaction. Therefore, we need one more A in order to meet the criteria for 2A. And so how would you do that? Well, you could just add a the second reaction. And so that second reaction also gets you the D. So now you have to worry about how you get the 2F. You can actually get the 2F if you reverse this reaction. If you were to say C plus E results in F, and that change in enthalpy would be negative 15, well, what happens is that the F from the second reaction and the F from the third reaction are going to add up to be 2F, and then the C cancels out with the C over here, and the E cancels out with the E over here. So what you're really left with is one of the first reaction, one of the second reaction, and one of the negated version of the third reaction. So let's add these all up. It's going to be negative 35 from the first reaction, plus 20 from the second reaction, plus minus 15 from the third reaction. Remember, the third reaction is going to be a negative since we reversed the order. We made it a reverse reaction. So if we were to add all these up, that would get you mental math. That's negative 30 kilojoules per mole. And that is answer choice B, and we are correct. The next thing I want to go over is the enthalpy of formation. So the enthalpy of formation is the change in enthalpy that occurs when 1 mole of a substance is formed from its component pure elements under standard state conditions. And so like this has different names. You can it might be sometimes called the standard enthalpy of formation or the heat of formation. And so there's an interesting thing here called standard state conditions. What are standard state conditions? Well, they vary for whatever you're looking at. So for gases, they're going to be at 1 atmosphere pressure. For liquids and solids, they're going to be the most stable, the most common and stable form of the compound at 1 atmosphere and 25 degrees Celsius. So if you're looking at something like carbon, well, the standard condition of carbon would be the graphite form instead of the diamond form, since graphite is far more common than diamond, obviously. And for solutions, it's just going to be a 1 molar concentration of the solution. So all these are going to be the standard states for their appropriate phase. Certain enthalpies of formation are going to have certain values. So for pure elements in their standard state, the enthalpy of formation is going to be 0. And this also includes diatomic elements like H2 or O2. These are going to have a change in enthalpy of 0. On the other hand, pure elements that are not in their standard states are not going to have a value of 0. So for example, diamond is going to have a change in enthalpy of formation of 1.88 kilojoules per mole, since diamond is not the standard state of carbon. Graphite, on the other hand, would have a enthalpy of formation of 0. For compounds, it's going to be based on the components. And we'll see how to calculate them in a little bit. But these are going to be far more complex to calculate than the other ones. So how would you go about calculating them? Well, we have a formula just like that's very similar to the entropy formula that we saw in last lesson. It's basically the sum of all the enthalpies of the products minus sum of all the enthalpies of the reactants. So if you look at this practice problem, where 2 CH3OH plus 3O2 react to form 2 carbon dioxide and 4 waters, how do we go about finding the enthalpy of formation of that? Well, let's start by finding the sum of the enthalpies of the products. Well, first of all, we have 2 carbon dioxides, and so since each carbon dioxide is negative 394 kilojoules per mole, we do 2 times negative 394, and then we add the 4 waters, and so that would be 4 times minus 242. So our products are going to come out to 2 times negative 394 plus 4 times minus 242. That is minus 1756 kilojoules per mole. And so that is for our products. Let's determine our reactants. So for reactants, it's going to be 2 times CH3OH. And so each of those are negative 201. So that would be that. And then we need to add the 3 oxygens. And remember, oxygen is diatomic and it's in its like purest form, in its more stable form. And so it would have a 0. So we would just do 3 times 0. So we really don't need to calculate that at all. And our value would come out to negative 402. Okay, now that we have both the products and the reactants, let's find the enthalpy of formation by subtracting them from each other. So minus 1756, and then we subtract the reactants side, so negative 402, and that's going to come out to, whoops, I had the answer up there, my fault, 1354 kilojoules per mole. So if you did some practice with the entropy stuff, then this is very similar. And a lot of things in thermodynamics are going to follow this general form where you just subtract products minus reactants. And this is how you calculate the enthalpy of formation. Another type of enthalpy I want to go over is bond enthalpies. So bonds are going to store energy. When you form a bond, energy is going to be released. And when you break a bond, energy is absorbed. So you have like a chart of bond enthalpies right here. And the thing is, although you have these values, the sign of the value is going to change whether or not you're forming or breaking that bond. So let's say we take the CH bond right here. If you were to form a CH bond, energy would be absorbed. So really your enthalpy would be negative 413. However, if you were breaking a bond, energy would be absorbed. So your enthalpy would be positive 413. And you need to take that into account whenever you're doing bond enthalpy calculations, which we're going to do right now. So we can calculate the change in enthalpy using bond energies. So our change in enthalpy of the reaction is going to be the sum of the bond energies of the bonds broken plus the sum of the bond energies of the bonds formed. Note that there is an addition here, because when we look at the bonds broken and formed, we're going to realize that the bonds that are going to be broken are going to result in a positive value, and the bonds that are formed are going to result in a negative value. So let's take this and let's do a bit of practice to kind of solidify this. So given the bond dissociation enthalpies below, what is the approximate change in enthalpy of formation of H2O? And so since it asks us for the enthalpy of formation, we're going to need to write out the reaction that's going to occur. The important thing about the enthalpy of formation is that at the end, you're going to have one molecule of the thing that you want produced. And so we know that the component parts that are going to make it are going to be H2 and O2, but these are not balanced. What you cannot do is add or make this more than a 1, right? You cannot have any other ratio or any other stoichiometric ratio in front of this that's 1. So what you're going to have to do is you're going to need to add a 1/2 to the O2 over here. So again, bond enthalpies are going to be, or determining the change in enthalpy using bond dissociation enthalpies is going to be the sum of the bonds broken, which is going to give you a positive value, plus the sum of the bonds that are formed, which is going to give you a negative value. So if we look at the bonds that are broken, it's going to be one HH bond, or rather, yeah, one HH bond. The O2 bond is actually a double bonded O. So we're going to have 1/2 of that, and that's it. For when we need to produce something, we're going to need to produce 1 molecule of H2O. And H2O looks like this. So really, it's just two OH bonds. So OH times 2. So bonds broken, these are going to be positive. So 432, that's the HH over here, plus the 1/2 times the oxygen that's double bonded. And now we add that to our the bonds that are formed. So it's going to be a negative value, and it's going to be 2 times the OH value, which is 467. Now, if you were to calculate this, you would get roughly 255, negative 255, sorry, kilojoules per mole. And that is answer choice D, which is the correct answer. One of the most important things here is that you cannot change the stoichiometric ratio of your product. You're going to have to cater the rest of the reaction to make sure that that product stays at a stoichiometric ratio of 1. And that is how you make like one of those equations for enthalpies of formation questions. There are a couple more enthalpies that I don't want to get like too much in depth into, but I do want to introduce them. These are going to be enthalpies of like phase changes. So enthalpies of fusion is the enthalpy change required to change 1 mole of a substance between solid and liquid states. Enthalpy of vaporization is between liquid and gaseous states. And enthalpy of sublimation is between solid and gaseous states. Now, enthalpy of vaporization actually has some uses. And so if you, the relationship between the temperature of a liquid and its vapor pressure can be determined if the enthalpy of vaporization is known. And you can do this using something called the Clausius-Clapeyron equation, where the natural log of the pressure of the second vapor is going to, over the pressure of the first vapor, is equal to the negative delta, the change in enthalpy of vaporization over R times, yeah, you get the rest. T stands for temperature, obviously, and the R constant in this case would be 8.3145. So let's do a bit of example. Let's do an example concerning it. What is the boiling point of water in a pressure cooker with an atmosphere of 2 atmospheres? The enthalpy of vaporization of water is 40.7 kilojoules per mole. So let's copy down our equation again, because it's pretty easy to forget. Vaporization over R times 1 over T2 minus 1 over T1. The thing is with this equation is that you need 2 states. In order to find out the boiling point of a liquid at a certain state, you need to know the boiling point of the water at a different state. And so the different state that we can use in this case is at 1 atmosphere, we know that water boils at 100 degrees Celsius. And 100 degrees Celsius is 370 degrees Kelvin. So we can actually input that information into our equation. So the natural log of the second pressure, let's say the second pressure is 2 atmospheres. So 2 over 1 equals the negative change in enthalpy, which we're told is 40.7 over R, which is 8.3145. And since we're using 8.3145, we actually have to convert this this value here into joules. Because before we had it at kilojoules, so let's turn this into joules. And then our T2, the second condition is at, well, we're trying to figure it out actually. And then the first condition is going to be at 373 degrees Kelvin. It's kind of some annoying math, but if you have a calculator, it's not too bad. If you calculate T2, you're going to get that it's about 394 Kelvin. And if you convert that into Celsius, that's going to be 121 degrees Celsius, which is answer choice B. And that is our answer. So the thing about this equation is that it allows you to compare states of liquids. So if you know the pressure and the temperature at which something boils in, If you're given a certain pressure, then you can figure out the boiling point of that liquid at that certain pressure as long as you're given the enthalpy of vaporization. And in this case, we use that to determine the boiling point of water in a pressure cooker with an atmosphere of 2 atmospheres. With a pressure of 2 atmospheres, sorry. And so that's all I have about enthalpy. That's all I have for this lesson. And I hope you learned something, and I hope you'll join me for the next lesson where we're going to go over Gibbs free energy and spontaneity. Thank you for watching, and I'll see you next time.